Hi everyone, Mrs. Patel Dane here for topic 8.3, weak acid and base equilibrium. So in topic 8.1 and 8.2, we had strong acids and strong bases. They completely disassociated when they were placed into water, so therefore we could use the essentially the pH H plus concentration square that we created during the last video. This time we have weak acids and weak bases. So these guys do not disassociate completely, meaning that you're still going to have some of the original acid or the original base left over. So here we're comparing and contrasting weak acids and bases. So let's complete the equation for this weak acid and label the conjugate acid-base pair. So with this, we have H3PO4 aqueous. We're going to add water to it. Anytime I use water or talk about water in this unit, I'm just going to write it as HOH. It's in liquid state. And this is in equilibrium with the products. So since H3PO4 is a weak acid, or an acid rather, it's going to donate its H plus right over here to that water, resulting in H2PO4. And then because that H plus, the H is a positive, this now becomes a negative ion. And that's an aqueous. Plus, then the leftover, we have H3O. And because, again, that extra H is positive, we're going to make this positive. So here is our acid. This is our base. Our water's acting as a base right here. And if this is in the reverse direction, this H3O plus would donate an H plus to the H2PO4 minus, resulting in what we have over here. So the H2PO4 minus is acting as a conjugate base, and the H3O plus is acting as the conjugate acid. So when we're talking about the acid-base pair, let's grab a pen, sorry. And we have this H3PO4 and the H2PO4 are a conjugate acid-base pair. And the water and hydronium ion are a conjugate acid-base pair as well. So if we are going to model this weak acid or a container of this, we'll have a container that has some water, so it's H2O. It also has H3O plus. It has some H2PO4 minus, and it also has H3PO4, which I have to squeeze in here. So it has all of those things in that beaker. Whereas if we had a strong acid, strong base, it would just have the leftovers, which would be like H plus and Cl minus if we're dealing with HCl. So let's do the K expression for this. Note that because this is an equilibrium, we can do a K expression. And this is the Ka because it's for an acid. So we have the concentration of our products, H2PO4 minus, times the concentration of our acid over the concentration of our H3PO4. And we are not including water in there because water is a liquid. So if we have a general equation for weak acids, we can say that we have HA, H being that extra hydrogen, the A being the acid, plus water, is in equilibrium with H3O plus and A minus. So that H gets donated to that water, making this the acid, this the base. And then over here, if we're going to go in the reverse direction, this H3O plus is the conjugate acid, and A minus is the conjugate base. So a general Ka expression for any weak acid would be Ka is equal to the concentration of H3O plus times the conjugate base over the acid. We also have something called pKa. So just like we had the potential of hydrogen or the potential of OH, we also have the potential of the equilibrium expression. So just like we found pH was the negative log of the H plus concentration. This is the, so pKa is equal to the negative log of the Ka. We also might need to find the percent ionization of a weak acid. So essentially, like, we want to know from in this beaker how much of the original acid would there be as opposed to how much of the conjugate base there will be. And each acid and each base completely different. So we might need to calculate that. And in here, we'll find the percent ionization is equal to the concentration of your hydrogen or your hydronium ion at equilibrium over the initial concentration of your acid. And because it's a percent, we multiply that by 100. So this is how to find the information for weak acids. Let's come on over to weak bases. Kind of the same thing here. In this case, you have NH2CH3, and that's a weak base. I'm going to add that to water. And I know if this is a base, this water is going to donate an H+. So this is going to act as the acid. This is going to act as the base. It's in equilibrium because it's not completely disassociating. This base now has an extra acid or an extra H+. So I can kind of put it in various spots, but I might just throw it right here at the beginning. NH2CH3. And because I'm adding an extra hydrogen on there, that's a plus charge. And then because this has given away an H+, I'm going to write this as OH-. So if I'm going to go in the reverse direction, this conjugate acid will donate an H+ to the conjugate base. So when we say that bases give off OH, this is what we mean. It's really because that base has taken on the H+ from water and made the rest of water a conjugate base. So even though you don't see any OHs in here, it's still going to be a base. If we model this, we'll show, maybe I'll make my container a little bit bigger so I can fit everything in here. I will see some NH2CH3. I'll see some water. I'll also have HNH2CH3 plus, and I'll have some OH minuses in there. A note about the waters, you can also disassociate those to be H plus and OH minus. So when we do that, let's say I get rid of this, H plus and OH minus, we still see that there's more OHs than there are H pluses, so therefore it's going to be basic. The Kb expression, so we have the equilibrium expression for the base is equal to the product, so HNH2CH3 times the concentration of OH minus over the base NH2CH3. And again, water is not included because that's a liquid in here. So a general equation for bases would be that you would have the base plus water, maybe write HOH in there, in equilibrium with HB plus and OH minus. So a general expression for this would be Kb is equal to the concentration of your HB times your concentration of OH minus. So the concentration of your conjugate acid and your conjugate base over the concentration of your base. And get used to like the lettering of this as well. To find the pKb, in this case, it's going to be the pKb is equal to the negative log of the Kb. And if we're going to find the percent ionization for this, the percent ionization is equal to the concentration of Hb at equilibrium over your initial concentration of the base. And because it's a percent, we have to multiply everything by 100. So if you recall, when we had the concentration of H plus times the concentration of OH minus, that equaled your 1 times 10 to the negative 14. The same thing is going to happen here for your Kw. So your Ka times your Kb is equal to 1.0 times 10 to the negative 14th. Recall that this is K, so it doesn't have a unit for it. And this is only at 25 degrees Celsius. So if we think about the relationship between pKa and pKb, if we think about pH and pOH, when we added those together, that equaled 14. The same thing happens here. The pKa plus the pKb is equal to 14. So again, hopefully you're listening and not just taking down random notes from a screenshot, because this actually explains how you can remember these values later on when you need them. So let's go to some questions on this. Caffeine is a weak base with a pKa value of 10.6. What is the pH of a 0.01 molar solution of caffeine? What is the percent ionization of the weak base? So we will put these into our good old friends, the rice table. Note, we didn't use the rice table for anything in the last topic because those were strong acids and strong bases, which completely disassociate. These, on the other hand, are going to be weak acids and weak bases, which will be in equilibrium. So I'll have my reaction C8H10N4O2 plus water. Ideally, you'd pause the video right here and finish off the equation. So then we're in equilibrium with OH minus, and we have to add an H to this, so maybe I'll throw it in the front. You might see it at the end. You might see it mixed in with making that H11. Whatever the case is, note that you just gotta find that extra H in there somewhere. And because this is, you're adding the H plus, this is now going to be a plus sign. So I have, first of all, I know that water is a liquid, so that's not going to have anything in here. And I know that the solution of caffeine started at 0.01 molar, and that's in molarity, so it's good to go. And I'm going to take out some value. Now, normally we would put in X for this, but because this is the base, let's throw in minus B. I'm going to add in plus B over here and plus B over here. So I end up with 0.01 minus B, and then B and B here. I also want to take a note. I went too far over on this side, but of that pKa, that's pKa, that's for an acid. This is a base. So we got to use some of those relationships we just talked about to make sure that we know how to get or convert between the two. So I know that 14 is equal to pKa plus the pKb. So if I want to find the pKb, I can say it's 14 minus the, what is that value? 10.6. 14 minus 10.6 should be 3.4. So that is my pKb, but now I want to find my Kb. So my Kb is equal to 10 to the negative pKb. And again, we didn't just go over this, but this is in the same pH square as we learned before about the relationships between like the concentration of H plus and the pH. It's the same type of relationship. We just raise that pKb to the by 10. Or sorry, raise 10 to that negative pKb. So we'll have 10 to the negative 3.4. So 10 to the negative 3.4. I'm going to use my second log, and that is negative 3.4. Should give me, let's see, 1, 2, 3, 4. So 3.98 times 10 to the negative 4. I am really wary of rounding here because I just don't want to get to a spot where like I've rounded too much and have an inaccurate answer. Let's see. So I'm going to find my values for each of these B's. Just like we did before, you have your concentration of OH minus times your concentration of HC8, H10, and 4O2 plus. Oh, caffeine's a wonderful molecule, but it's very large in there. All right, over the concentration of the initial weak base, C8, H10, and 4O2. So from here, you should be able to solve for the rest of this, right? I know my Kb is equal to 3.98 times 10 to the negative 4. By the way, ideally we'd be pausing right here, solving the rest of this, and then checking in with me at the end. So I have my concentration of my B times my B over 0.01 minus B. If I were to multiply and distribute with that 0.01 minus B, I would have to use the quadratic equation to get rid of x. So I don't want to do that. Instead, I can say, assume B is negligible. That means that we have this is equal to B squared over 0.01. So 3.98 times 10 to the negative 4. And let's throw this into our calculator. So 3.98, and then use the second EE button, negative 4, times 0.01. And notice I put the stuff that's in scientific notation in parentheses because I'm just trying to save myself some issues and prevent any errors. So then I want to take the square root of that, and I get 1 point, let's see if I'm thinking about this, 1.99 times 10 to the negative 3. And that's in concentration or molarity. So this means that we have the concentration, how am I going to do this, of that B right over here for OH. So the OH minus is equal to, the concentration of OH minus is equal to 1.99 times 10 to the negative 3 molar. But this wants me to find the pH. So from here, I can use that square that I realized back in my old stuff, which, let me grab that if I can find it. So the stuff from the last topic. Second. And you should have this with you. If we haven't memorized how to do this, make sure you have it. So right now I'm here. I want to get to down here. So I can go down and over or across and down. So let's say I do, let's do the pOH is equal to the negative log of the OH concentration. So it's equal to the negative log of 1.99 times 10 to the negative 3 molar. So negative logs can answer. And note that I'm just doing like that answer from before that's already in my calculator. So if your number's slightly off than mine, that's why. So this is my pOH. Now I want to find my pH. So I can then say that pH plus pOH is equal to 14. So my pH is equal to 14 minus 2.70. So 14 minus 2.7 gave me 11.3 as my pH. Does this make sense? Well, sure, we have a base. So the pH should be above 7, but it's a weak base. So it's actually not going to be like, we know bases are from like a little bit above 7 to 14. This is partway through. It's not reaching all the way up to 14, and that makes sense because this is a weak base. You're still going to have some of the conjugate acid, conjugate base in there as well. So having something moderately basic is actually like fine for this answer. All right, so let's take a peek at the next problem. The pKa of hypochlorous acid, HClO, is 7.54. What is the pH of 0.100 molar solution of HClO? Do the same exact thing as we did before. So let's throw this into a rice table. Oh, and again, ideally, you would be doing this on your own. I'm just here as like back. Like, let's assume right now, you paused, you did this whole problem, now you're just checking with me. That is what makes a student who knows what they are doing, as opposed to somebody who's just following what's written on the board. You want to be the person who knows what you're doing. All right, so water is a liquid, so I'm going to leave it at that. I have here that I have 0.100 molar for my acid, and I have 0 for my initial concentrations of my conjugate acid and conjugate base. I know this is going to be subtracted by an X, an unknown. This is an acid, so I'll put in minus A. I'll put in, oopsies, plus A here. Sorry, my bad. So 0.100 minus A, and this is A, this is A. So I have here that the pKa is 7.54. I can't put pKa in, but I can put Ka in. So my Ka is equal to 10 to the negative pKa. And again, I'm just kind of using the same relationships as I realized from POH to OH or pH to H+. Same type of relationship. So I've got 10 to the negative 7.54. 10 to the negative 7.54. All right, a bunch of zeros. And you can always change this into scientific notation. Let's see if I can, yeah, there we go. So I've got 2.88 times 10 to the negative 8 as my Ka. And note how I just did that, by the way, for the TI-30X2S. So I just went to second and then science engineering, and I could just pick out which one I wanted. And this one's scientific notation, so I'm going to stick to that. Note that other stuff will be in scientific notation, so I might need to either convert out of it or just deal with it, and that's fine. So don't forget to put your equilibrium expression in there. I have seen a lot of folks miss out a point on questions because they did not put this in here. There's been points where College Board has been really kind and given people points for putting in that really, really easy expression. So don't be lazy. I say that with all the kindness in the world. Please don't be lazy and not put that in there. All right, so, whoopsies. We can say assume A is negligible. So then you have 2.88 times 10 to the negative 8 is equal to 8 squared over 0.100. So let's clear that out. Again, I'm going to put these in parentheses, 2.88 second EE negative 8 times 0.1. And I'm going to take the square root of that while I'm here. So A is equal to 5.37 times 10 to the negative 5th. And we want to figure out the pH for this. So this is essentially going to be the concentration of my H3O plus. So that's equal to concentration of H3O plus. Oops, sorry, getting off screen there. And so I know that my pH is equal to the negative log of my H plus or H3O plus concentration, the same thing. So negative log of 5.37 times 10 to the negative 5th. So here I've got negative log of 5.37 times 10 to the negative 5th. And so I've got 4.27 as my pH. Double checking, that is what I want to solve for. So that is that answer right there. Perfect. There are going to be two more problems on the next page. And these are fairly, oh, I'm sorry. One thing I forgot to do. Whoops. Forgot to do the percent ionization for each one of the, or for the one up here. My bad. Sorry. So I am going to do the percent ionization. Coming back to, find that paper. Oh, over here. For number 4, I wanted the percent ionization of the weak base. So this is my percent ionization formula right here. And maybe I'll do that in different colors. So that way I can differentiate that from here. Percent ionization is equal to the HB plus at equilibrium over the initial concentration of B times 100. And I'm just getting my values over from the table and some of the stuff that I've already found out. So I know that my HB at equilibrium is 1.99 times 10 to the negative 3. Again, if you round it a little differently, as long as it's somewhere around there, that's totally okay. And then my equilibrium here was 0.01 minus B. We're assuming that B is negligible. And if we think about it, that's times 10 to the negative 3. So if we think about 0.01 minus something to the 10 to the negative 3, that is still going to be pretty teeny tiny. So that you can actually omit there. But for good measure, I'm just going to make sure I have it in there. it won't do anything. It won't affect your final answer too much. So I've got 1.99 second e minus 3 divided by 0.01 times, and I'll put this in parentheses as well, just to make sure that I don't mess up anything with my formula. Cool. And then times 100. Again, note, I had this in scientific notation. So if I do it this way, I think I messed up on that one. Sorry, my bad. So actually, let me omit this because that might make it a little bit better. 1.99 -3. I think I may have multiplied the two. I don't know. 0.01, times 100. There we go. That's better. So this is 19.9, and this is percent. So it's percent ionization of 19.9, meaning that the original substance, 19.9 of it, percent of it ionized into this. The rest of it is left as this. So the majority of this substance is still staying like this. So the next question didn't ask about our number 5 didn't ask about ionization, but you'd follow that same path as well. Number 6 just asks about the ionization. This, again, is fairly straightforward to solve. So we should get, and I'm going to, we're at the pretty lengthy part of this video. So what I'm going to do is give you the H plus concentration, or sorry, the like the HA, the weak acid of this should be 1.57 molar. So do all the work, show all that work to get to there. And if that is an issue, by all means, and you've talked to some people, please let me know. Do note, though, that you have to plug this back into, like, let's say we're dealing with this problem, right? You'd have to plug it right back into here to figure that out. So make sure you do that. And then your percent ionization would be at the end. I got 1.05%. Check your work, check my work when we were in class together if we need to. But if you didn't get that, and a majority of the other people didn't get that, and people that you trust, not just anybody, but people that you trust, then we'll revisit that. And then down here for the formic acid question, I think they just wanted the pH. So I got a pH of 1.93. Get this down here. So double check your stuff, do this, and let's make sure that we get this all set. All right, and let me know in class if we have any questions. Take care. Bye.